Hi, my name is Evan. Today we are going beyond the basics of structured concurrency, exploring how structured tasks can simplify realizing useful behaviors. Before we get started, if you're new or want to review structured concurrency, feel free to watch the Explore Structured Concurrency in Swift and Swift Concurrency behind-the-scenes sessions from WWDC23. Today, we'll review the task hierarchy and how it unlocks automatic task cancellation, priority propagation, and useful task local value behaviors. Then we'll cover some patterns with task groups to help manage resource usage. Finally, we'll look at how all of these come together to facilitate profiling and tracing tasks in a server environment. Structured concurrency enables you to reason about concurrent code using well-defined points where execution branches off and runs concurrently and where results from that execution rejoin, similar to how if blocks and for loops define how control flow behaves in synchronous code. Concurrent execution is triggered when you use an async let, a task group, or create a task or detach task. Results rejoin the current execution at a suspension point, indicated by an await. Not all tasks are structured. Structured tasks are created using async let and task groups, while unstructured tasks are created using task and task detached. Structured tasks live to the end of the scope where they're declared, like local variables, and are automatically canceled when they go out of scope, making it clear how long the task will live. Whenever possible, prefer structured tasks. The benefits of structured concurrency discussed later do not always apply to unstructured tasks. Before we dive into the code, let's come up with a concrete example. Suppose we have a kitchen with multiple chefs preparing soup. Soup preparation consists of multiple steps. The chefs have to cut ingredients, marinate chicken, bring the broth to a boil, and finally cook the soup before it's ready to serve. Some tasks can be performed in parallel, while others must be done in a specific order. Let's see how we can express this in code. For now, we'll focus on the makeSoup function. You may find yourself creating unstructured tasks to add concurrency to your functions, and then awaiting their values when necessary. While this expresses which tasks can run concurrently and which cannot, this is not the recommended way to use concurrency in Swift. Here's the same function expressed using structured concurrency. Since we have a known number of child tasks to create, we can use the convenient async let syntax. These tasks form a structured relationship with their parent task. We'll talk about why this is important shortly. MakeSoup calls a number of asynchronous functions. One of them is chop ingredients, which takes a list of ingredients and uses a task group to chop all of them concurrently. Now that we're familiar with MakeSoup, let's take a look at the task hierarchy. Child tasks are indicated by the colored boxes, while the arrows point from parent task to child task. MakeSoup has 3 child tasks for chopping ingredients, marinating chicken, and boiling broth. Chop ingredients uses a task group to create a child task for each ingredient. If we have 3 ingredients, it too will create 3 children. This parent-child hierarchy forms a tree, the task tree. Now that we've introduced the task tree, let's start identifying how that benefits our code. Task cancellation is used to signal that the app no longer needs the result of a task and that the task should stop and either return a partial result or throw an error. In our soup example, we may want to stop making a soup order if that customer left, decided they wanted to order something else, or it's closing time. What causes a task cancellation? Structured tasks are canceled implicitly when they go out of scope, although you can call cancel all on task groups to cancel all active children and any future child tasks. Unstructured tasks are canceled explicitly with the cancel function. Canceling the parent task results in the cancellation of all child tasks. Cancellation is cooperative, so child tasks aren't immediately stopped. It simply sets the isCancelled flag on that task. Actually acting on the cancellation is done in your code. Cancellation is a race. If the task is canceled before our check, MakeSoup throws a soup cancellation error. If the task is canceled after the guard executes, the program will carry on preparing the soup. If we're going to throw a cancellation error instead of returning a partial result, we can call task check cancellation, which throws a cancellation error if the task was canceled. It's important to check the task cancellation status before starting any expensive work to verify that the result is still necessary. Cancellation checking is synchronous, so any function, asynchronous or synchronous, that should react to cancellation should check the task cancellation status before continuing. Polling for cancellation with is cancelled or check cancellation is useful when the task is running, but there are times when you may need to respond to cancellation while the task is suspended and no code is running, like when implementing an async sequence. This is where with task cancellation handler is useful. Let's introduce a shift function. The cooks should make soups as orders come in until the end of their shift, signaled by a task cancellation. In one cancellation scenario, the asynchronous for loop gets a new order before it is cancelled. The makeSoup function handles the cancellation as we defined earlier and throws an error. In another scenario, the cancellation may take place while the task is suspended, waiting on the next order. This case is more interesting because the task isn't running, so we can't explicitly poll for the cancellation event. Instead, we have to use the cancellation handler to detect the cancellation event and break out of the asynchronous for loop. The orders are produced from an async sequence. Async sequences are driven by an async iterator, which defines an asynchronous next function. Like with synchronous iterators, the next function returns the next element in the sequence, or nil, to indicate that we are at the end of the sequence. Many async sequences are implemented with a state machine, which we use to stop the running sequence. In our example here, when isRunning is true, the sequence should continue emitting orders. Once the task is cancelled, we need to indicate that the sequence is done and should shut down. We do this by synchronously calling the cancel function on our sequence state machine. Note that because the cancellation handler runs immediately, the state machine is shared mutable state between the cancellation handler and the main body, which can run concurrently. We'll need to protect our state machine. While actors are great for protecting encapsulated state, we want to modify and read individual properties on our state machine, so actors aren't quite the right tool for this. Furthermore, we can't guarantee the order that operations run on an actor, so we can't ensure that our cancellation will run first. We'll need something else. I've decided to use atomics from the Swift atomics package, but we could use a dispatch queue or locks. These mechanisms allow us to synchronize the shared state, avoiding race conditions, while allowing us to cancel the running state machine without introducing an unstructured task in the cancellation handler. The task tree automatically propagates task cancellation information. Instead of having to worry about a cancellation token and synchronization, we let the Swift runtime handle it for us safely. Remember, cancellation does not stop a task from running. It only signals to the task that it has been cancelled and should stop running as soon as possible. It is up to your code to check for cancellation. Next, let's consider how the structured task tree helps propagate priority and avoid priority inversions. First, what is priority and why do we care? Priority is your way to communicate to the system how urgent a given task is. Certain tasks, like responding to a button press, need to run immediately, or the app will appear frozen. Meanwhile, other tasks, like prefetching content from a server, can run in the background without anyone noticing. Second, what is a priority inversion? A priority inversion happens when a high priority task is waiting on the result of a lower priority task. By default, child tasks inherit their priority from their parent. So assuming that makeSoup is running in a task at medium priority, all child tasks will also run at medium priority. Let's say we have a VIP guest who comes to our restaurant looking for soup. We give their soup a higher priority to ensure we get a good review. When they await their soup, the priority of all child tasks is escalated, ensuring that no high priority task is waiting on a lower priority task, avoiding the priority inversion. Awaiting a result from a task with a higher priority escalates the priority of all child tasks in the task tree. Note that awaiting the next result of a task group escalates all child tasks in the group, since we don't know which one is most likely to complete next. The concurrency runtime uses priority queues to schedule tasks, so higher priority tasks are selected to run before lower priority tasks. The task keeps the escalated priority for the remainder of its lifetime. It's not possible to undo a priority escalation. We effectively satisfied our VIP guest with a speedy soup delivery and got a good review, so our kitchen is starting to get popular now. We want to ensure that we're using our resources effectively and notice that we're creating a lot of chopping tasks. Let's investigate some useful patterns for managing concurrency with task groups. We only have space for so many cutting boards. If we chop too many ingredients simultaneously, we'll run out of space for the other tasks, so we want to limit the number of ingredients getting chopped at the same time. Going back to our code, we want to investigate the loop creating the chopping tasks. We replace the original loop over each ingredient with a loop that starts up to the maximum number of chopping tasks. Next, we want the loop collecting results to start a new task each time an earlier task finishes. The new loop waits until one of the running tasks finish, and while there are still ingredients to chop, adds a new task to chop the next ingredient. Let's distill this idea down to see the pattern more clearly. The initial loop creates up to the maximum number of concurrent tasks, ensuring we don't create too many. Once the maximum number of tasks is running, we wait for one to finish. After it finishes and we haven't hit a stopping condition, we create a new task to keep making progress. This limits the number of concurrent tasks in the group, since we won't start any new work until earlier tasks finish. Earlier, we talked about chefs working in shifts and using cancellation to indicate when their shift was over. This is the kitchen service code handling the shift. Each cook starts their shift in a separate task. Once the cooks are working, we start a timer. When the timer finishes, we cancel all ongoing shifts. Notice that none of the tasks return a value. New in Swift 5.9 is the with discarding task group API. Discarding task groups don't hold on to the results of completed child tasks. Resources used by tasks are freed immediately after the task finishes. We can change the run method to make use of a discarding task group. Discarding task groups automatically clean up their children, so there is no need to explicitly cancel the group and clean up. The discarding task group also has automatic sibling cancellation. If any of the child tasks throw an error, all remaining tasks are automatically canceled. This is ideal for our use case here. We can throw a time to close error when the shift is over, and it will automatically end the shift for all chefs. The new discarding task group automatically releases resources when a task finishes, unlike normal task groups where you have to collect the result. This helps reduce memory consumption when you have many tasks that don't need to return anything, like when you're processing a stream of requests. In some situations, you'll want to return a value from your task group, but also want to limit the number of concurrent tasks. We covered a general pattern for using the completion of one task to start another, avoiding a task explosion. We're making soup more efficiently than ever, but we still need to scale up more. It's time to move production to the server. With that comes challenges of tracing orders as they are processed. Task local values are here to help. A task local value is a piece of data associated with a given task, or more precisely, a task hierarchy. It's like a global variable, but the value bound to the task local value is only available from the current task hierarchy. Task local values are declared as static properties with the task local property wrapper. It's a good practice to make the task local optional. Any task that does not have the value set will need to return a default value, which is easily represented by a nil optional. An unbound task local contains its default value. In our case, we have an optional string, so it's nil and there is no cook associated with the current task. Task local values can't be assigned to explicitly, but must be bound for a specific scope. The binding lasts for the duration of the scope and reverts back to the original value at the end of the scope. Going back to our task tree, each task has an associated place for task local values. We bound the name Sakura to the cook task local variable before making soup. Only make soup stores the bound value. The children do not have any values saved in their task local storage. Looking for the value bound to a task local variable involves recursively walking each parent until we find a task with that value. If we find a task with the value bound, the task local will assume that value. If we reach the root, indicated by the task not having a parent, the task local was not bound and we get the original default value. The Swift runtime is optimized to run these queries faster. Instead of walking the tree, we have a direct reference to the task with the key we're looking for. The recursive nature of the task tree lends itself nicely to shadowing values without losing the former value. Suppose we want to track the current step in the soup making process. We can bind the step variable to soup in make soup and then rebind it to chop in chop ingredients. The value bound in chop ingredients will shadow the former value until we return from chop ingredients, where we will observe the original value. Through the powers of video editing magic, we've moved our service to the cloud to keep up with the demands for soup. We still have the same soup making functionality, but it's on a server instead. We'll need to observe orders as they pass through the system to ensure they're being completed in a timely manner, and to monitor for unexpected failures. The server environment handles many requests concurrently, so we'll want to include information that will allow us to trace a given order. Logging by hand is repetitive and verbose, which leads to subtle bugs and typos. Oh no, I've accidentally logged the entire order instead of just the order ID. Let's find out how we can use task local values to make our logging more reliable. On Apple devices, you'll want to continue using the OS log APIs directly, but as parts of your application move to the cloud, you'll need other solutions. Swift Log is a logging API package with multiple backing implementations, allowing you to drop in a logging backend that suits your needs without needing to make changes to your server. Metadata Provider is a new API in Swift Log 1.5. Implementing a metadata provider makes it easy for you to abstract your logging logic to ensure that you're emitting consistent information about relevant values. The metadata provider uses a dictionary-like structure, mapping a name to the value being logged. We want to automatically log the order ID task local variable, so we check to see if it was defined, and if it is, add it to the dictionary. Multiple libraries may define their own metadata provider to look for library-specific information, so the metadata provider defines a multiplex function, which takes multiple metadata providers and combines them into a single object. Once we have a metadata provider, we initialize the logging system with that provider, and we're ready to start logging. The logs automatically include information specified in the metadata provider, so we don't need to worry about including it in the log message. The logs show as order 0 enters the kitchen, and where our chefs pick up that order. Values in the metadata provider are listed clearly in the log, making it easier for you to track an order through the soup making process. Task local values allow you to attach information to a task hierarchy. All tasks except attached tasks inherit task local values from the current task. They are bound in a given scope to a specific task tree, providing you with low-level building blocks to propagate additional context information through the task hierarchy. Now we'll use the task hierarchy and the tools it provides us to trace and profile a concurrent distributed system. When working with concurrency on Apple platforms, Instruments is your friend. The Swift Concurrency instrument gives you insight into the relationships between your structured tasks. For more information, check out the session Visualize and Optimize Swift Concurrency. Instruments also introduced an HTTP traffic instrument in the Analyze HTTP Traffic and Instruments session. The HTTP traffic analyzer only shows traces for events happening locally. The profile shows a gray box while waiting for a response from the server. So we'll need more information to understand how to improve the performance of our server. Introducing the new Swift Distributed Tracing package. The task tree is great for managing child tasks in a single hierarchy. Distributed tracing allows you to leverage the benefits of the task tree across multiple systems to gain insight into performance characteristics and task relationships. The Swift distributed tracing package has an implementation of the Open Telemetry Protocol, so existing tracing solutions like Zipkin and Jaeger will work out of the box. Our goal with Swift distributed tracing is to fill in the opaque waiting for response in Xcode instruments with detailed information about what is happening in the server. We'll need to instrument our server code to figure out where we need to focus. Distributed tracing is a little different from tracing processes locally. Instead of getting a trace per function, we instrument our code with spans using the WithSpan API. Spans allow us to assign names to regions of code that are reported in the tracing system. Spans don't need to cover an entire function. They can provide more insight on specific pieces of a given function. WithSpan annotates our tasks with additional trace IDs and other metadata, allowing the tracing system to merge the task trees into a single trace. The tracing system has enough information to provide you with insight into the task hierarchy, along with information about the runtime performance characteristics of a task. The span name is presented in the tracing UI. You'll want to keep them short and descriptive so that you can easily find information about a specific span without clutter. We can attach additional metadata with the use of span attributes, so we don't need to clutter the span name with the order ID. Here we've replaced the span name with the function directive to automatically fill the span name with the function name, and used the span attribute to attach the current order ID to the span information reported to the tracer. Tracing systems usually present the attributes while inspecting a given span. Most spans come with HTTP status codes, request and response sizes, start and end times, and other metadata, making it easier for you to track information passing through your system. As noted on the previous slide, you can define your own attributes. For more examples of how you can leverage spans, please check out the Swift Distributed Tracing Extras repository. If a task fails and throws an error, that information is also presented in the span and reported to the tracing system. Since spans contain both timing information and the relationships of tasks in the tree, it's a helpful way to track down errors caused by timing races and identify how they impact other tasks. We've talked about the tracing system and how it can reconstruct task trees using trace IDs, and how you can attach your own attributes to a span. But we haven't started working this into a distributed system yet. The beauty of the tracing system is that there's nothing more that needs to be done. If we factor a chopping service out of our kitchen service, otherwise keeping the same code, the tracing system will automatically pick up the traces and relate them across different machines in the distributed system. The trace view will indicate that the spans are running on a different machine, but will otherwise be the same. Distributed tracing is most powerful when all parts of the system embrace traces, including the HTTP clients, servers, and other RPC systems. Swift distributed tracing leverages task local values, built on the task trees, to automatically propagate all of the necessary information to produce reliable cross-node traces. Structured tasks unlock the secrets of your concurrent systems, providing you with tools to automatically cancel operations, automatically propagate priority information, and facilitate tracing complex distributed workloads. All of these work because of the structured nature of concurrency in Swift. I hope this session excited you about structured concurrency and that you'll reach for structured tasks before using unstructured alternatives. Thank you for watching. I can't wait to see what other useful patterns you'll come up with using structured concurrency. Soup.